Okay, so today we're going to be doing chapter 6 of AP Calculus BC, and that's mainly more applications of derivatives and integrals. We'll be talking about exponential functions, logarithmic functions, inverse trigonometric functions, and then some other topics like implicit differentiation and inverse functions and the mean value theorems. In the end, we'll be talking about improper integrals. So we're going to start with exponential and logarithmic functions. So the reason why these are in chapter 6 and not earlier is because these are a bit different than regular functions like polynomials and rationals. So that's why these are in this later chapter. First of all, exponential functions, it's basically a to the power of x, where a is any constant, but it's usually going to be e to the power of x, where e is the exponential constant, and e is approximately 2.718. The reason why e is special is because it's called the natural exponential, e to the power of x is called a natural exponential function. And e just has a bunch of applications. One common one is in compounded interest, because continuously compounded interest has the formula, the value is equal to the principal amount, the original amount, times e to the power of RT. And the reason why we use e is because e is equal to the limit as n approaches infinity of 1 plus 1 over n to the power of n. There are a few other variations of writing this, but this is probably the most common. Now, what happens if you write an to the power of bn? So we're basically modifying it a bit with this. What this is basically going to be is, instead of just being e, it's going to be e to the power of a times b. You're basically just taking it to the power of the product of these two new constants you added. So that's a bit of an introduction into e. Why is it useful in calculus? Well, one important thing is that the derivative of the function e to the power of x is itself. Derivative of e to the power of x is just e to the power of x. So that's why it's really useful in calculus, because when you just want like an easy function is just e to the power of x, you can take the derivative of a to the power of x, where a is any constant. And the formula for this is a to the power of x, but it's not as simple as e to the power of x, because you also have to multiply by ln of a. Now, this is the more general formula for exponential functions, and you can actually plug in e for a, and you get e to the power of x times ln of e. And ln is actually something called the natural logarithm. It's log base e. And from previous math courses, you probably know logarithms. It's the inverse of exponents, and we'll be talking a bit more about them soon. But ln is log base e, because e is the natural exponential constant. So ln is natural logarithm, so it has e as its base. So when you take log base e of e, you just get 1. So ln of e is 1, and you just get e to the power of x. So you can actually use this to show that the derivative of e to the power of x is itself. So that's the derivative of exponential functions, but you can also take the integral of exponential functions. And these are very similar. The integral of e to the power of x dx, as you might imagine, is, again, itself, e to the power of x, and then plus c, because we're taking the general antiderivative. So we always have to keep that in mind. But you can also take the integral of any function a to the power of x dx, and you can, apply a bit of chain rule, and you get a to the power of x over ln a plus c. So that is the formula for the integral of an exponential function, any exponential function. It works for any of these. Now, what about logarithms? So you can also take the derivative of logarithms, and you can also take the integral of logarithms. When you take the derivative of ln x, you're going to get 1 over x. So a little preface of logarithms: when you have log base b of x, this basically is equal to y. This basically means that x is equal to b to the power of y. You might have learned that in a pre-calculus or algebra course, but just prefacing this with that is pretty important.
Hola.
Yeah, so this is just an introduction into logarithms, and the reason why we write this is because it's the inverse of an exponent, and we're going to be talking about derivatives of inverse functions later in this video. So you can actually use that to sort of prove this. So first of all, derivative of ln x is equal to 1 over x. And obviously in this video, since it's just a review video, I'm not going to go into the proofs or anything. I'm just going to give you the formulas and give you examples of them. So the reason why this is, you can find an online proof or something, but this is just one derivative to memorize. And as you might imagine, there's the formula for the derivative of log base b of x. And this is going to be 1 over x times ln b. So it's kind of similar to the derivative of an exponential function, but you just have to multiply by ln b in the denominator since it's 1 over x. Of course, you can also take the integral, but not the integral of ln x. I'm going to mention that in a minute, but first, what if you take the integral of 1 over x dx? We know that ln x becomes 1 over x when you take its derivative, so when you take the integral, it's going to become ln x. However, it's going to be ln absolute value of x. Because when you look at the graph of 1 over x, you see there's a negative portion, but ln x is not defined for negative x because ln x, the graph of it, is just this. There's no negative portion, which means this entire piece of the graph is not going to be defined for ln x, which is why you do absolute value to mirror this and make it a positive, which means ln x will always be defined for all x. So that's why you always have to remember it's ln absolute value of x. Pretty important to remember that because you might get an error if you just do like ln negative 2. And finally, like I said, we'll mention the derivative of ln x, or sorry, the integral of ln x. And this is a bit more complex than you might imagine. It's going to be x times ln x minus x plus well.
Don't care. I don't care.
And the reason why it's a bit complicated, again, there's proofs online, but you can take the derivative of this function to see that the integral of ln x is really this. You basically undo the antiderivative, you get the derivative. So derivative of this, let's actually do it here. So x times ln x, you do product rule. So derivative of x is just 1, so it becomes ln x. And then you have to do plus x times derivative of ln x. Derivative of ln x, we said was 1 over x. So x times 1 over x is just 1. And then minus derivative of x is 1. And then derivative of a constant is 0, so just plus 0. So we get ln x plus 1 minus 1. The plus 1 minus 1 cancel it, and we get ln x just as we imagined. So the integral of ln x is really x ln x minus x plus c. So that's exponential functions and logarithmic functions, derivatives and integrals. I'll go over a few example problems now so we can learn it a bit better. So let's say we have the function f of x is equal to 2 to the power of x squared minus 4. The derivative of f of x, f prime of x, is going to be equal to, so we know the formula is a to the power of x times ln a. So we can write 2 to the power of x squared minus 4 times ln 2. But chain rule, remember, we have a function in the exponent, not just x, which means we also have to multiply this by the derivative of the exponent. X squared plus minus 4, the derivative of x squared is 2x, and then minus 4 just becomes 0 because it's a constant. So we're going to get 2 to the power of x minus 4 times ln 2 times 2x. Theoretically speaking, you could combine it. You're going to get 2 times 2 to the power of x squared minus 4. You're going to get 2 to the power of x squared minus 3, because when you multiply 2 by that, you're just adding 1 to the exponent. So you can do that times ln 2 times x. On a test, I think either should work because you can either not simplify it fully or you can simplify it fully, and it sort of loses the kind of the meaning, because what's good about this first form is that you see 2 to the power of x squared minus 4, 2 to the power of x squared minus 4. You see a connection. And then in this case, you see x squared minus 3, and it's not that the connection isn't really there. So the first one is better to like show the connection. The second one is better to simplify it in case you really do need to simplify. And then another example, integral of 1 over 3x dx. It's not that complicated. It's not really a chain rule. You just take out a 1/3 and you do integral of 1 over x dx. We already know the integral of 1 over x is ln of absolute value of x, and then you just add the plus c, and that would be your answer. This one is more of just like memorizing the formula. The integral of 1 over x is ln absolute value of x. So that's exponential and logarithmic functions. One more set of formulas to memorize is inverse trig functions. So while we're talking about exponentials and logarithms are the inverses of each other, we can also say that they're inverse trig functions, namely inverse sine, inverse cosine, inverse tan, inverse cotangent, inverse secant, and inverse cosecant. Obviously, there are the derivatives of the trigonometric functions, sine, cosine, tan, cotangent, secant, cosecant, but this is the inverse of them, and it's not what you might expect. These don't really have to do with the trigonometric functions. Instead, they have to do with right triangles. So I'll just show you how to derive one of them. So in case you don't really want to memorize this, you can derive them on the spot. You just have to change up the values for the derivation. So let's start with inverse sine. Inverse sine takes in the ratio of two sides and outputs an angle. So let's say y is this angle that we want to find, and x is the ratio of opposite to hypotenuse. So since it's inverse sine of x, this should be x and this should be 1. So we do x divided by 1 gives you x. Of course, you can do 2x and 2, but that's just complicating it. You can just stick with x and 1 for the derivation. If this is x and this is 1, this is a right triangle, so we get x squared, square root of x squared plus 1 as our hypotenuse. And, oh, sorry, I was doing tangent because I was doing opposite over adjacent. Instead, it should be opposite over hypotenuse. So hypotenuse should be 1, opposite is x, so this is square root of 1 minus x squared. Sorry, the adjacent would be square root of 1 minus x squared because of the Pythagorean theorem. So now what we want to do is we want to find the derivative of inverse sine, and that's basically going to be, we write sine of y is equal to x. You can also write, you use this adjacent, so cosine of y is equal to square root of 1 minus x squared. And then what you can do is you can use implicit differentiation. So actually, we didn't learn implicit differentiation yet, so I'll hold off on this proof for now. Instead, I'll just show you the formulas and then come back to implicit differentiation. The formula for inverse sine is going to be 1 over square root of 1 minus x squared. And you can actually see where the formula comes from. Square root of 1 minus x squared is cosine. So you sort of see that you get square root of 1 minus x squared from that cosine y. And again, I'll prove it to you later once we learn implicit differentiation. But for now, it's just a bunch of memorization. Inverse cosine is going to be negative 1 over square root of 1 minus x squared. So basically, the negative of whatever sine was, it's actually the exact same thing except for the negative. Inverse tangent is going to be 1 over 1 plus x squared. Inverse cotangent, as you might expect, is negative 1 over 1 plus x squared. And finally, inverse secant is going to be 1 over absolute value of x times square root of x squared minus 1. And inverse Cosecant, no surprise, -1 over absolute value of x times square root of x squared minus 1. So these are just a bunch of formulas. You might think that sine and tangent are not related whatsoever, but the derivation is basically the same. You just use different variables since tangent is different than sine. Again, I'll show the derivation later once we learned implicit differentiation. But these are just a few of the formulas that you should probably memorize, either that or derive them. Moving on, finally, we get to implicit differentiation. Implicit differentiation is basically when you have both a y and an x in the equation, and you basically need to take the derivative of that. So think of it like a circle. X squared plus y squared is equal to 25. That's a common circle. You want to find the slope function for the circle. You can't really do that with what we learned. Of course, you could isolate for y. You get something with a plus or minus square root. You can just use that as two separate functions and then find it that way. That is a very inefficient way to do it. Instead, you can use implicit differentiation. What that basically is you first differentiate both sides with respect to x. So you basically do d dx of the entire equation, not just one side of the equation. So let's start with x squared. X squared, d dx of x squared is just 2x. No problem there. D dx of y squared. So that's a bit tricky. But think of y as a function of x. So it's actually going to be a chain rule somewhat. We get y squared, so it becomes 2y. But since y is a function of x, and we just took a derivative of y squared, we do chain rule. So we multiply it by y prime, or as you can write it, dy dx. So that's just chain rule right there. Think of y as a function f of x. When you do f of x squared, you take the derivative, you get 2 times f of x. And then because of chain rule, you multiply by f prime of x. That's basically what's going on down here. We're doing 2y times dy dx because that's the derivative of y with respect to x. And finally, the derivative of a constant is just 0. So we have this equation. Now, you might be a bit stuck, but what we do is we basically isolate for dy dx, since that's what we were looking for. We want the slope function, which is dy dx. So you move the 2x to this side, you get 2y times dy dx is equal to -2x. And then dy dx, you divide by 2y, you can cancel off a 2, you get -x over y. And that is the slope function for a circle. Obviously it has y in it. That's because the original equation had y in it. If you solved for y and then found the derivative of that, you would get the same answer, except you just have to plug in y here. So let's say if we do solve it, we get y is equal to square root of 25 minus x squared, obviously plus or minus. You just plug that in here and you're actually going to get the same answer. But this is a much easier way to do it, which is why we're learning implicit differentiation. There are a bunch of examples of this. For example, 2xy plus 8y squared minus 3x is equal to 6y plus 11. This is a very complex equation at first, but with implicit differentiation, you can actually simplify it a lot. First, we have 2xy, product rule. First, we start with 2x. Derivative of that is just 2, so 2 times y. And then we keep the 2x. Derivative of y is just 1, but then we have to multiply it by dy dx because of chain rule. Then we have derivative of 8y squared is 16y times dy dx because of chain rule. Minus derivative of 3x is 3, so we keep that. This derivative of this is 6 times dy dx. And then 11 just becomes 0, so we ignore it. Move all the dy dx's to one side, so you can factor that out. 2x, 16y. And then actually minus 6 when you bring that over to this side. And this is equal to, you bring the 2y to that side and the plus minus 3 to that side, becomes -2y plus 3. Now you just divide and you get dy dx is equal to negative 2y plus 3 over 2x plus 16y minus 6. And that's your derivative. A lot of times, problems would ask for d squared y over dx squared. That's basically the second derivative, which you can do in this step. You just take the derivative again. You get a bunch of dy dx's. You get a bunch of d squared y over dx squareds. You isolate for this, the second derivative, and you're going to get some expression on the other side with x's, y's, and dy dx's. For every dy dx you see, just plug this into that, and it's going to look really complicated for this function. For this one, not so much. You just, and I'll actually show you an example with this one. So let's say we go back to this step where we have 2x plus 2y times dy dx equals 0. So derivative of 2x is just 2, and then plus chain rule d2y, derivative of that is 2, and then times dy dx because of product rule. And then we keep the 2y, and then we take the derivative of dy dx. So that gives you the d squared y over dx squared. And again, equal to 0 because that doesn't change. And we now have a d squared y over dx squared. And that times 2y is equal to, we move this over to the other side, negative, and then 2 plus 2 times dy dx. Cancel off a 2 from all sides, and we get d squared y over dx squared is equal to negative 1 plus dy dx over y. Final step, plug in what we got for dy dx back into here, and we're going to get d squared y over dx squared is equal to negative 1 plus, well, technically minus because it's x over y, 1 minus x over y, complex fraction, so we can just multiply by y over y to clear it, and you get y minus x over y squared. And it doesn't look that complicated because it's a pretty simple function. That's going to be your second derivative. Obviously, for this one, it's going to be very complicated because you already have a pretty complicated first derivative. So it's not that fun to do that. Like I promised, we're going to get back to the proof for the inverse trig derivatives. We start with y as the angle and x as the ratio of opposite to hypotenuse, x to 1. This becomes 1 square root of 1 minus x squared. And we say sine of y is equal to x. That's basically what we're doing because we said x sine inverse of x is equal to y. So we're basically taking the sine of both sides, and we get x is equal to sine of y. To find the derivative, we do implicit differentiation because we have an equation with both y and x. We start with this side because it's a lot simpler. We get 1 equals, inverse of sine is cosine, and we keep the y inside. And it's that times dy dx. Yeah, and we are going to, because dy dx, because of chain rule, we take the derivative of y. So we isolate for dy dx. It's going to be 1 over cosine of y, which is secant of y. And now it looks like we're a bit stuck because we have a y in it. We only want x because remember, these formulas only had x in them. How do we get there? Well, we just know that it's going to be secant, which is hypotenuse over adjacent, because cosine is adjacent over hypotenuse. Secant is 1 over that, so it's going to be hypotenuse over adjacent. We know hypotenuse is 1. We know adjacent is square root of 1 minus x squared. So we get that dy dx is going to be 1 over square root of 1 minus x squared. And that's how we prove the formula. you can do the same thing for each of the 6 ones. So I'm not going to show it, obviously, because it'll take too much time. But this is just how you would derive it in case you don't want to memorize the formula and actually want to derive it on the spot. I wouldn't recommend that because it takes some time, especially if you kind of forgot how to derive it, because it's not that simple, not as simple as one would expect. So I would memorize it just in case. And then if you want to double check on the test or something, you can derive it. So that's that. We have a few more things to talk about. Derivatives of inverse functions. So given a function f of x, its derivative, let's say g of x, is equal to the inverse. Sorry, the inverse of f of x is equal to g of x. And we want to find g prime of x at some point a. Let's say it's a comma b for g of x. Since f is the inverse of g, it's going to be b comma a for f of x. So that's something to keep in mind. The slope, the derivative at this point is basically going to be 1 over f prime of g of a. That's the formula. A simpler way to write it, g of a, well, when you plug in a into g, you get b, so you can replace g of a with b, so it's inverse 1 over f prime of b. So at this point, b comma a, that's why it's important that we switch those places when we found f of x. F prime of b is just the slope at this point b, so it's just going to be 1 over that slope. It looks more complicated than it actually is. It's like saying we have some function here. This is the line y equals x, so the inverse is going to be like this. At, let's say, 3 comma 6, the slope is this for the actual function. So at 6 comma 3, it's going to be 1 over that slope for the inverse function. So that's quick and easy. Most of these problems have tables of like different values, and you have to like plug in values and check. So I obviously can't show an example of that here because it'll take too much time, and it's more like an FRQ than an MCQ kind of problem. One of the final topics is going to be mean value. So the mean value of a function is basically all of the terms, or the mean value of like a sequence is going to be the sum of the terms divided by the number of the terms. But if you have a function like this and you want to find the mean value of it, it's basically going to be the sum of all of them. So if you find the sum, that's basically another way of saying the area under the curve. And it's going to be divided by the number of terms. So it's basically going to be the initial, the final minus the initial. So the formula for the mean value is going to be 1 over b minus a times the integral of f of x dx. Integral from a to b, it's a definite integral. So that's the mean value. You say it's the average value of f of x. So that's what you would call the mean value. You can find it for any function, and you're going to get the average value of that function over time. Now, there are 2 mean value theorems according to the book. Technically, only one of them is an actual mean value theorem. The other one is not really called a mean value theorem usually, but since it has to do with a mean value, it's called a mean value theorem in the book. And the actual mean value theorem is about derivatives, and it says that if f of x is continuous on the closed interval ab and differentiable on the open interval ab, you have the average rate of change of a function over some interval is f of b minus f of a over b minus a. That's the definition of average rate of change over an interval. Now the mean value theorem for derivatives states that there exists some c within a comma b. So this e symbol basically means belongs to, such that f prime of c is equal to this average rate of change. And I should probably include prime over there to show average rate of change rather than average value. Basically saying you have an interval, the secant line is basically going to be the average rate of change. So the slope of the secant line, at least one point in that interval has the same slope as the secant line. So if you have something like that, the secant line is this. There's like this one. This one is equal. This one is equal. There's actually quite a few in this example, but it just says there has to be at least one. Then there's the mean value theorems for integrals, which says that on a continuous interval f a comma b, if f of x is continuous on the open interval a comma b, closed interval a comma b, then again, the mean value is this. There exists some f of c where c belongs to ab, the open interval, such that this is equal to the average value. In other words, you have a function like this. The average value is here. There has to be at least one value that is equal to the mean value of that function over the interval. Mean value theorem for derivatives on the left-hand side, mean value theorem for integrals on the right-hand side. And then we've got Rolle's theorem, which is basically an application of the mean value theorem. Again, similar criteria. It says that if f of a equals f of b, then there exists some c which belongs to a comma b, such that f prime of c equals 0. Basically, there's got to be a minimum or maximum somewhere. It's like saying you have this function where the two values are equal. There's got to be a minimum or maximum somewhere. In other words, basically the slope of the secant line is 0 here, which means there has to be a tangent line that's equal to 0 at some point. It's basically saying the mean value theorem, but applied specifically. So you're not going to use that much. It's just in certain cases. Finally, last topic is improper integrals. Improper integrals are integrals that basically can be infinite. There are two types. Type 1 is an integral with infinity in the bounds. So you're going to get something like from 1 to infinity of 1 over x dx. And the reason this is allowed is because when you look at this graph, 1 over x, it actually like goes down to 0. So it's possible that there is a value. What you would do is you would basically write limit as b approaches infinity of integral from 1 to b of 1 over x dx. And now you just solve this antiderivative like normal. You say 1 over x, well, the antiderivative of that is ln absolute value of x. So you do ln absolute value of b minus ln absolute value of 1. Ln absolute value of 1 just gives you 0. So you're just going to get ln absolute value of b. So limit as b approaches infinity of ln absolute value of b is actually going to diverge because it will approach infinity. If it does not approach infinity, it's going to converge to a number, and you can actually solve for that number using limits. But this one diverges. Type 2 is going to be when the bounds don't contain infinity, but it actually does go towards infinity. So you have like 1 to 3 of 1 over x minus 2 to the power of 1/3 dx. The graph of this looks something like this, because at 2 there's a vertical asymptote. Since the denominator has a 2, you're going to get something that looks a bit like that. So it goes to infinity over here, and again you can use limits and the antiderivative to find it. Improper integrals seem a bit tricky at first, but it's just find the antiderivative and then limits. You're basically going to separate the integral into a limit, and then you're going to introduce a variable into the bounds. So that's basically all of chapter 6. Do you all have any questions? Then that's it for chapter 6. It's basically more applications of derivatives and integrals. And yeah, I'll see you for chapter 7. Bye.